Well, first of all, many functions can be written in the form a sub 0 plus a to the x plus ax squared plus x cubed, uh, pretty much an infinite polynomial. And polynomials which can be written in this form are called power series, where they are centered around a value of 0. So once you can successfully write a function as an infinite polynomial, they are called power series. And the Maclaurin's expansion is just simply one of those types of series that allows for functions to be written as a polynomial. The Maclaurin series is used to approximate values of a function, and this approximation, this Maclaurin expansion, it happens to be extremely accurate. But of course, with different theorems and so on, there are always conditions. So with respect to the Maclaurins, even though the approximation is very accurate, the values of x must be very close to 0. They should be hovering very close to 0 if you were to use this expansion, right? So pretty much in a nutshell, this expansion is just used to generate a polynomial of this form here that you can see on screen. And you will have this, actually you have several different types of expansions, because you have Maclaurins for exponential functions and log having standard expanded forms in your formula sheet. So today's lesson is really to teach you the application of the basic expansion that you can see on screen. So let's get into it. Now, 2 points to note before we even begin that I want you guys to always remember about Maclaurins is that the approximation, so I'll put that point right here, using this expansion, your approximation is going to be very accurate. That's 1 point to note. And the second point, our condition should be used if your x values are very close to 0. Pretty close to 0. All right. Let me just correct that there. Okay. So essentially, what does the Maclaurin's expansion look like? Well, this is your standard form here. You would be given a function, and you would be asked to write it as an infinite polynomial series, hence the ... after the last term, well, supposedly last term there. And of course, when you are adding terms in a sequence, they become a series. So you can find the sum of that, sum of the sequence there, right? Given that by this function. Now, if you observe the Maclaurin's expansion, you'll notice that you are seeing f prime, f double prime, f triple prime. Now, generally in maths, that means that the function is being differentiated. So you'll notice that the first term starts off with your function at 0. Then your second term involves your function being differentiated and the value obtained at 0. Then your function being differentiated a second time and that value being obtained at 0 again. So it's just a repetitive pattern you pick up on, as well as the coefficient. The coefficient in front each term will start. The coefficient in this first term is missing because it's x raised to the power of 0 over 0 factorial. And you all know anything raised to the power of 0 is 1. So if we were to write a coefficient, say over here, then that would essentially be x to the power of 0 over 0 factorial, and that's just essentially 1. So that's why the coefficient in front here is missing. However, the second term is there. You'll see x to the power of 1, and of course that's over 1 factorial. Then it keeps on increasing to the power of x to the n over n factorial. So it's pretty similar, I'd say, to a binomial expansion, or all different types of binomial expansions pretty much, except in this case you have to consider where your coefficient is kind of similar to your n choose r kind of standard form, but your main part of your term comes by differentiating the function again and again and again repetitively at 0. All right, so I wanted you guys to take note that when you are actually using Maclaurin's expansion, besides the basic conditions, make sure that if they have not explicitly asked you to use Maclaurin's expansion and you're looking at a function and wondering, can I use Maclaurin's expansion? For example, if you have the function e to the x and you're wondering if you can rewrite this function as a polynomial, an infinite polynomial, well, first of all, you should tick off 3 of these main points to note here. So looking at your function, is my function differentiable? Well, yes, we can differentiate e to the x. We know that the first derivative of e to the x is also e to the x. So check. Is my function, does my function exist at x equals 0? Let's test it. F at 0 will simply be equal to e to the 0, which gives us a value of 1. So check, that holds. What about the third point? All f sub n, rather f to the power of, not the power of n, but being differentiated at all levels of differentials must exist at x equals 0. So we can test this over and over again. The second differential of e to the x will also be e to the x. The third differential will be e to the x as well, and so on. And they said all derivatives must exist at x equals 0. So let's see. After the first differential, does let me just erase this here. Let me write it properly. After we differentiate the first time, does our function exist at 0? Well, since the derivative is still e to the x, then at 0 we'll get e to the 0, which is still 1. And that case will similarly hold for the second differential. You'll get the same thing, and so on for the third derivative. All right, so guys, it seems like our third condition is going to hold. Now, once you're able to successfully meet all of these conditions, it means that your application of using Maclaurin's expansion for whatever function you are given is a success, and you may continue. So having spoken a little bit about a brief history about when you should use Maclaurin's expansion, exactly what it looks like, the fact that the approximation tends to be very accurate, let's look at some questions as to how we can actually apply this expansion to get infinite polynomials. So let's take a couple questions here. All right. So for example, let's look at a simple case where we are given, let's take a trig function. Let's just say we have a trigonometric function of the nature sine x. And they ask us to find the Maclaurin series, or what they're asking essentially is, can you find the infinite polynomial series, right? And they're giving us a limit to find the Maclaurin series for this function, but up to the term, let me say in x cubed. All right, we'll stop at x cubed. All right, so they want us to use the Maclaurin's expansion to expand this up to the term in x cubed. So kind of similar to the binomial expansion in terms of they are asking you to calculate the expansions only up to a certain term, but yet, of course, the binomial comes with a power, and this is just a straight up trigonometric function. So one of the first things I would do in answering this question is, of course, make sure that function exists at 0. So we have our function, and our function is sine x. So I want to make sure that my function exists at 0. Now, you all know that sine of 0 is just simply equal to 0. So yeah, it does exist. And I'm going to get into my first derivative and see what happens. I think I'll put it side by side. The first differential of sine gives us cos of x. And does my differential exist at 0? Let's test it. Well, cos of 0, yes, it does have a value. Cos of 0 is 1. Let's continue to the second derivative. If you differentiate cos x, of course, you'll get negative sine x. And let's find out if our function exists, our second derivative exists at 0. So once again, negative sine 0 gives us 0. Of course, you'll be using your calculators, but standard, you guys should recall that, sine of 0, cos of 0 is 1, sine of 0 is 0. All right, now the question, says we're going up to the x cubed term here, right? So let's keep pushing at it. That's 1. First derivative, second derivative, third derivative. So we need to keep going. All right, so we're going to go on to the derivative here. Now, if we were to differentiate this another time, we would get, now the differential of sine is cos, but we're going to plop back down that existing sign that came with the question before, and then differentiate sine gives us cos x. A lot of students tend to make this mistake. All right, don't forget your sign that originally existed in front. And finally, we are going to find out if this function exists at 0. Well, this derivative, and that is simply negative 1. Cos 0 is 1, so negative cos 0 is negative 1. Okay, beautiful. So we have found all the terms up to x cubed. How do I know I found up to the x cubed? Because remember, if you go back to your expansion, all right, the x, this term over here, let me highlight it. X to the nth power is related to the nth derivative as well. So if they're asking you to find the coefficient or step up to the x5th term, then that would mean that you also need to find the 5th derivative. That's how you would be able to recognize how many differentials you need to go up to. That's a good point to note. Okay, so heading back down to our question, we just need to apply the standard expansion and put this answer together. So Maclaurin's expansion goes like this. Functions written as an infinite polynomial series takes the form f of 0 as your first term plus x squared on 2 factorial by your second derivative plus x cubed on 3 factorial by your third derivative. Of course, you know, this keeps going on and on and on for terms beyond the power of 3, and so on, right? So let's get into it here and see what's happening. So we have on the left-hand side our function. Our function is given by sine x. So on the left-hand side, we'll write back our function as sine x. And on the right-hand side, what values did we get? Well, f of 0 was given by 0. So our first term actually worked out to be 0. Then we're going to add x. And what was our first derivative at 0? Our first derivative at 0 was actually 1. Then you have x squared on 2 factorial. All right, now we're going to find out what's the second derivative at 0. We got the second derivative at 0 to actually be equal to 0 again. So we are going to substitute that value of 0 in here. Plus, then we have x cubed on 3 factorial. You can plug this into your calculator, you'll get 6. Similarly, 2 factorial, you would get 2. All right, and cleaning this up here, finally, the third derivative at 0, we're getting -1. Plus, dot, dot, dot. If they had access for more terms, we would have continued with our answers. So cleaning this up here, let's see what we have been able to come up with using this Maclaurin's expansion. So this goes away, we'll just get x. This goes as away because we're multiplying by 0. And we have minus x cubed all over 6. So notice that, and of course, we need to show that our expansion is continuing after. Right, so we have successfully answered our question. They asked us for the terms of this up to x cubed, and we have applied our Maclaurin series, and we have generated our answers x subtract x cubed on 6. Sometimes people leave this as 3 factorial. You should essentially expand everything to the simplest form possible. So I would advise you guys to change your 3 factorial to a 6. Sometimes you can never tell what can cancel. So it's always good to expand those factorials. So this is an example of how you would apply the Maclaurin series to a trigonometric function. And it would also, you guys should take note at the end of this video, I'll be showing you some standard Maclaurin expansions, because there are some standard ones that you can memorize sometimes, but if the question is more of a proof, then you would need to do your full working. All right, so I'm going to get a little more into the, let's see, complex forms of questions that can come with Maclaurin's. So let's just see if we can't go up anymore. That's okay. I think I have no more space. I'm gonna have to erase my board. All right, guys, so we're gonna do some erasing. Boom. That was easy. Nothing beats an online whiteboard, guys. This is awesome. All right, so we're gonna get, I think we were on question. This should be question 2. Yeah. Okay. So I just showed you guys an example of like a trig. I can show you guys an example of perhaps where we have negative power. So what if we have a function like this? We have x plus 2 all squared. Now you can rewrite this as x plus 2 to the power of -2. And of course, you can use the binomial expansion to work out this question using the binomial expansion. Take note that if you had to using the binomial expansion here, right? Remember, it needs to be in the form of 1 plus something. So you would need to rearrange this interior. First of all, you could rewrite it as 2 plus x. And then, of course, remember, the binomial comes in the form 1 plus x. Sometimes people have 1 plus a. Variables are arbitrary here. So you need to make sure that this term is always 1. So you would need to pull out that, and it's being raised to the power of -2. So once you factor that outside of brackets, you need to pull that power that it was being raised to within brackets. And then finally, inside brackets, you would divide each term by your 2. So you would have 1 plus x all over 2. And then for a question like this, you would be able to apply your binomial expansion for this part of your question here. And once you're successful in applying your binomial expansion, when it's dealing with a negative power, you would have to remember to multiply your entire answer by 2 to the power of -2, which is simply 1 over 2 squared, which is a quarter, right? And you would use your binomial expansion to expand the interior of this brackets. Now, that's one way of doing this question, to produce a polynomial. And you can try using the binomial expansion and see what answer you generate. But essentially, you should get the same answer if you were to use the Maclaurin for this question. So as a side note, you guys can take some time, apply the binomial to this question, see what results you get. And now what we're going to do is we are actually going to use the Maclaurin here, and you can then compare your answers. All right, so let's get into it. All right, I think I'll use green. All right, so applying Maclaurins. Now, of course, you have to look out for those conditions, right? But remember, those conditions are going to naturally pop up when you realize your function cannot be differentiated at 0. So your differentiation skill has to be on point here. So if you tend to be weaker in differentiating, you need to do back some reviews on different types of differentiation. But once you are doing the power series, especially Maclaurin's expansion, you need to have that strength in being able to differentiate. Okay, so moving forward here, the first thing we are going to do is we're going to find our function at 0. Okay, so our function at 0 is going to be, what's that, 0 plus 2? You don't have to use a calculator for this. Pretty much 0 plus 2 is 2, so that's just a quarter. All right, that's just a quarter. Then comes the fun part. We are going to differentiate. So, wonder if I should write this answer side by side. So we have our function being given by x plus 2 to the power of -2. Now, if you didn't write over your question as an exponent like this, and if you left it as a fraction form, I guess you could have used the quotient rule, but using the quotient rule in a question like this is actually going to produce a very long answer. Oh, I did not state we are going to expand this function, let me just write it down, expand this function. Okay, up till, let's just do the x cubed term again, so it doesn't get very long. All right, so we're going to expand this function up to the x cubed 2. All right, I forgot to write my question. Okay, getting ahead of myself there. So our function is given by this, and I wrote it as an exponent because it's going to be easier to differentiate as considering this as a chunk. So my first derivative is simply going to be, remember when you're differentiating a chunk, you just simply bring your power in front and you have to reduce. Remember, you're reducing for differentiation, reduce the power by 1, so that actually gives us -3. And of course, you multiply by the derivative of whatever was inside of brackets. Now, the derivative of x plus 2 is simply 1. So this is our final differential. And our first differential at 0 would work out to be 0 plus 2 to the power of -3. That is -2 all over 2 to the power of 3. So that works out to be negative, I believe, 1 over 2 2s are 4, because the 2's here would cancel and this would get, right. So you should get -1/4 for your first derivative at 0. So Maclaurin's can be applied clearly because the function was differentiable. All right, let's test it for the second derivative. Now, to help me, I am actually going to write my previous derivative right here so I can see what I'm working with. Make it all clear and nice. Now I'm going to get into differentiating this using my basic normal differential skills. I'm going to bring my power down in front as a coefficient. So we already have -2. So that's -2 times -3 giving me +6. And we leave our brackets untouched. We reduce our power by 1. And of course, we multiply by the differential of the brackets, which happens to be 1. So finally, my second derivative at 0 will be, what's that equal to? I think that's a 6 over 2 to the power of 4. And this reduces to, let's see, 2 2s are equal to 16. I think that's 3 over 8. All right, so we're going up till the x4 term here. So we have one more to go. All right, so finally, for the sake of simplicity, I'm going to write on my third differential again so I see what I'm working with. All right. And now I'm going to differentiate or attempt to differentiate. The moment your function is not differentiable, you cannot apply your Maclaurin's expansion, okay? So attempting to differentiate, we'll get -24 x plus 2 to the power of -5. The derivative of your brackets is just 1. And finally, whoo, you can breathe now. You sub that 0 in there. And that I'm just going to tell you, you guys can try it out, but this works out to be -3/4. Oh boy, wow. That was a lot of work. You need to breathe, but you'll survive. Once your differential game is on point, and your substitution game is on point, your calculator game is on point, your minimal making mistakes game is on point, that's a lot of points, but they will come together to produce a very beautiful answer at the end of the day. So take your time. Maths is not as terrible as some people like to think of it. It's very straightforward. It's just all about sectioning off your answer, letting your answers flow from sentence to sentence, and making sure you don't jumble things up too much. Always section them off. If you've noticed, I created little sections on screen, and that's kind of a nice tactical method to identify when you make mistakes. Sometimes, you know, you can check each section and identify a mistake easier. All right, guys. So we're going to put this answer together and let's see what happens. I'll try to write my answer on screen where you can see where I'm pulling everything from. So I'm going to write my answer in red. So pulling everything together using that using our standard format. I'll write down my standard format for you guys one more time. F of 0 plus x, f prime of 0 plus x squared over 2 factorial, f double 0 plus x cubed over 3 factorial, f triple prime. at 0 plus dot dot dot. Now what's our function? Our function is originally given by 1 all over x plus 2 squared. What was our first value? Well, our first value was a quarter, so a quarter goes here. What was our first derivative at 0? Minus a quarter. So I'll change this sign and I'll rewrite it as minus a quarter x, so minus x on 4. Then we have x squared on 2 factorial. 2 factorial is just 2, multiplied by our second derivative. Our second derivative was given by 3/8, so that's 3 over 8. So I'll bring this denominator to 16 and I'll write 3x squared over 16 instead. Okay, so I'm going to write 3x squared over 16. Okay, and then finally, we have x cubed over 3 factorial. So that's x cubed over 6. And our third derivative worked out to be minus 3/4. So our answer is going to be minus, okay, it's going to be minus 3/4 by that x cubed over that 3 factorial. 3 factorial is 6, so 6 by 4 is, oh, I made a mistake, by the way. This is supposed to be 3 over 4, not 3 over 8. Just use my black to correct that. See how easy it was to identify your mistake sometimes? You have to be very, very careful when doing these questions. 2 by 2. Oh, no, I was correct. I was definitely correct. I thought I made a little mistake there. Right, and then finally, this one actually works out to be 3, where was I? Got lost. And this happens in exam and it's okay. Sometimes you just need to simply take your time. Let's take our time and break this down. All right, so taking our time, we had x cubed over 3 factorial, and 3 factorial is 6. And in brackets, we are going to write our 3/8. Okay, that's 3 over 8. And that gives us 3 over, I think that's 6 8 to 48. Somehow I think I am making a mistake in substitutions here. But I'm going to rewrite this as 3 over 48. Now, of course, if you have seen my little error that I am stuck on, you can go ahead and you can leave your comments below and you can say, Miss, I see your error. I am definitely seeing it here, because somehow I am noticing that there is an error. Perhaps I'll go through it again. We'll see. Okay. But yeah. So we have 3x cubed over 48. And I think that's our answer there. 3x cubed over 48. So let's just double check this one over here. And let's just make sure we're doing fine. So we had, oh, I saw it. I kept on substituting 3 over 8. That is our second derivative. That's what I knew. I was looking at something. I knew this was making sense, because usually there's a pattern with the Maclaurin series. You'd never literally get like 1, 1, 3, and then the next 3 over 48. Something looked funny, and I knew it. So you guys, you see how it's very important to double check your work. It happens. It doesn't mean you don't know what you're doing. It just means that, you know, you made a little mistake somewhere, and that's only human. So we're going again, attempting this. We had a plus x cubed over 6, and our third is actually negative a quarter down here. Here it is. It's negative 3/4. Wow. And this, my friends, simplifies into negative 3 over 24. Of course, 3 into 3, 1, 3 into 6 is 2. So that's negative x cubed over 8. Right? 4 by 2 is 8. So let's write that back as negative x cubed over 8. All right, so that is negative x cubed over 8. And I am so happy that I have identified that mistake in this video, because then I would have had to do a lot of editing. Okay, guys, so yeah, so it happens. Okay, so that's great. And finally, what I'll have you guys know is that, once again, from the beginning, I was saying if you were to apply your binomial for when you have negative powers, you could be able to see that at the end, you are supposed to generate the exact same answer as if you were to use the Maclaurin's expansion. If your differentiating skill is on point, some students may prefer to use Maclaurin's instead of the binomial expansion. However, please take note of what your question is intentionally asking you to do. A lot of questions I get sometimes is, what about if we were given a numerator that was not 1, as in this case? Well, then when you are differentiating, you would have to use your quotient rule, right? So when you're using Maclaurin's, take note that any type of differentiation can pop up. It can be for trigonometric functions, it could be for Ln functions, it can be any type, pretty much. I think I would have liked to, perhaps in the next video, I may do a tutorial on some more questions, but I want to highlight different types of expansions that are standardized, and I want to show you guys how you can apply it to extend your answers. All right, so for example, I have here, let me just share with you guys. All right, so let's make him right. All right, nice, beautiful. So here are some Maclaurin expansions of some common functions. Notice they all have a condition. All right, because remember, you want that x value to be very, very close to 0. So you usually identify the use of this function when your x values tends to be very close to 0, right? Now, what if they gave you the functions being in the form of e to the x or sine x or cos x, or any of these forms pretty much on the left-hand side here? Then if they do, instead of actually working out the full derivatives step by step, you can actually just use these already worked out solutions. They are called standard expansions when you are given some standard functions. So if the question gives you, for example, a function, say, for example, let's see which one. What if they give you a ln of 1 plus 2x? Well, if you observe down here, this is a standard expansion for ln of 1 plus x. So by extension, you can actually apply this. You can apply this standard expansion to extend to suit the question they have given you. If you notice that in the standard expansion, they have x, but in your question, you have 2x. So what you can do is recognize that x is simply being replaced by 2x. And you can alter, yes, you can actually alter your standard expansion to look as follows. All right, so by extension, 1 plus 2x can now be written as replacing your x with 2x everywhere you see it. So in the standard expansion, you had your question beginning with x, so you will replace that with 2x. Then subtract x squared, so you'll replace that with 2x squared over 2. Then x cubed will be replaced with 2x all cubed over 3. Use your brackets. It's not just the x alone, it's the whole entire chunk. And then finally, the last term, the x4 would be replaced with 2x to the power 4 all over 3. And this is how you would extend your standardized function if they are ever given. This case applies for all. The same thing with cos x. If you were given cos 2x, then instead you would have cos, for the second term, you would have 2x squared, 2x4, and so on. So pretty much it's just about being able to extend based on what you are given. You can actually use the different forms to extend your functions. All right, guys. So I hope that helps a lot. And these standard expansions are also present on your formula sheet. So I think a good point to note at the end of this lesson is students who are writing exams. You may sometimes think that the formula sheet is only important for exam time, but it will help to be very familiar. It will help to be very familiar with your formula sheet. Whichever country you come from, whichever exam, if you're writing A-levels, if you're writing GCSE, if you're writing CAPE, no matter wherever, whichever is your Board of Examinations Council, your formula sheet must contain some sort of formulas. And it's very, very helpful to know which formulas actually are on them. And you work alongside with your formula sheet when you're revising, because it can actually be a comfort to you knowing that, you know, you have help on board. Your formula sheet is like an assistant, you know, like a little secret assistant in the examination room, you know. And just be very familiar with what it has, because sometimes it can save lots of you guys from making mistakes when you assume that, you know, the formula sheet doesn't help, and you assume that you have to memorize all these different expansions on your own. No, the application of maths is what is at the core of everything. You know, a lot of people tend to think memorize, just be able to apply and substitute. No, maths is all about the application, right? Do you know when you need to use something? Do I know the conditions under which I can use this formula? A lot of students do questions and they just write out solutions like robots, and that's what makes it the world more difficult. It just makes everything so difficult. So sometimes it just helps to really understand your topic, understand when and where it is used for, and know your formula sheet well, so you can kind of eliminate memorizing a lot of stuff that you don't have to memorize in the first place. It clears your mind of clutter, and it allows for your understanding of how you should flow from step by step when answering your questions, guys. So that's the end of this session on Maclaurin's expansion. I hope you guys are doing well. A couple of students messaged me and told me to just go ahead and use my personality in the videos, because they said, Miss, that's not you. You are a bubbly person. You tend to be very funny. We were looking forward to seeing that aspect of you on the videos. And I was like, okay, I'll try to incorporate it next time. You know, so yeah, I think from now on, and as I produce more videos, I will definitely be keeping that point in mind. So guys, I am going to go on with my life, and I'm going to figure out some stuff here, and you guys are going to go on with yours and watch this video. Be sure to like, subscribe, and share. So I thank you guys. It was good to be with you. Goodbye.